I'm Tim Ventura, and we're joined today by Dr. John Parmentola, a physicist, adjunct staff member at the RAND Corporation, and formerly senior vice president at General Atomics, where he led the company's Energy and Advanced Concepts Group. He joins us today to talk about the future of fusion energy and his senior leadership role at the DIII-D National Fusion Facility. So John, welcome. And let me start out with some background info. You are a PhD physicist from MIT with decades of experience in defense, energy, and other sectors. So what led you to a leadership role in fusion at the DIII-D National Fusion Facility?
Yeah, well, it wasn't so much D3D that brought me there. It was more General Atomics. And that gets traced back to my career, which has been very varied in terms of the things that I've done in various sectors of the national R&D enterprise. And I would trace them all back to MIT because when I was there, I had some great mentors that took an interest in me. And I not only did serious fundamental basic science research, but I also got involved in science and technology policy issues. The important people in that regard were Herman Feshbach, who was a legend in nuclear physics, and he was department head at the time. And also Bernard Feld, who had a long history in the Manhattan Project. And quite fortuitously, I got involved in a couple of science and technology projects at MIT while I was doing research in elementary particle physics and nuclear physics. And I ran into a brilliant individual by the name of Richard Garwin. And Dick opened my eyes as to how you could use science as a fundamental basis of formulating government policy. And the experience that I had was being a part of a study on particle beam weapons. This was before Reagan's famous SDI speech back on March 23rd, 1983, I think it was. And so I participated in this study, and it was really interesting. I was sort of the, I don't know, calling me maybe a cherub at the time, who worked out all the calculations that Dick laid out on a blackboard. And so that sort of inspired me to understand and appreciate the role science can play in science and technology policy. So that guided me through my career. I went and did academic research, started a whole research program by myself at the Department of Energy, but at the same time, I was working in science and technology policy. I wrote a book on space defense with a center in Washington, DC called the Roosevelt Center for American Policy Studies. And I then took a sabbatical and went to the John F. Kennedy School of Government as a fellow there. And I worked with Ashton B. Carter, who's the former Secretary of Defense. This was around 1988.
Okay.
And I did some very important work in arms control verification there. It was original, completely original work I did. And from there, I went to the MITRE Corporation, which is sort of in between government and academia. And then I transitioned into government. And I spent time at the US Department of Energy. I then went to the US Army. I then, I think I was the second or third employee at the Defense Threat Reduction Agency when it was stood up around, trying to think, 1999, when it was launched. And I played a role there. I did some really important work there. And then I went back to the Army after 9/11. and I think I would say my time with the Army was the most productive time in my entire career in terms of contributions that were foundational at the Army, and a lot of it still exists today. So at that point, I figured, well, let me round out my career and get some experience in the private sector. And so this job came along at General Atomics, and it sounded really interesting. One of the major projects that was being pursued at that time was a revolutionary new compact, fast gas reactor, fission reactor that the group there was pursuing. And so I decided it was the right time. And, these jobs are rare. They're rare jobs.
Yeah.
You can't find jobs like this very easily. And when people ask me, well, what do you do as senior vice president at General Atomics in energy and advanced concepts? I says, well, I lead the third Disney World, and so, every day was a day of creativity and working with incredibly gifted and talented people who are dedicated problem solvers. And so that's how I wound up. And D3D was a part of the whole enterprise there in energy advanced concepts. And, I had a background in nuclear physics, so I understood the basic fundamentals about fusion. And, but I'm not a plasma physicist. So that was something that I had to pick up bits and bobs of while I was there. But, there are plenty of really talented people there who, educated me on various aspects of fusion and plasma physics.
Yeah. So now your role was mostly leadership, right? Administrative, managerial. And now what were some of the main accomplishments that you had in terms of fusion research during your time there?
Well, I would say one of the main ones was, at the time, there was a phenomenon that occurred inside of a fusion reactor at the edge of the plasma where it meets the first wall, where there were current spikes that occurred that could damage the first wall. And, if you wanted to think about these, sort of not exactly the same, but if, you look at the surface of the sun, you see matter get spewed out, in various directions, and these are kind of instabilities that occur that sort of percolate, at the surface. And so the plasma has these characteristics where you get these current spikes. So the question was, could you control them? And D3D had a long history of inventing technology to stabilize and control plasma's instabilities on short time scales. And this was a challenge. And the researchers there met the challenge and figured out a way of smoothing these out so as to limit the damage on the walls. Mm. The other thing about D3D was it was there as a resource to help address certain research issues associated with ITER. And of course, a major part of its program was dedicated to that, and trying to reduce the risk associated with ITER. The other aspect of D3D, which I took I would say a strong leadership role in, was you can't make progress in science unless you have new instruments to be able to measure things that either with greater accuracy than you did before, or new measurements to try to challenge the theorists to be able to understand and predict the phenomena associated with plasmas. And so we undertook a major effort to develop new instruments at D3D. And this feeds theory, and then theory feeds experiment, and it increases the synergy between them to make progress and advance the science. But there's also another very important aspect that always stuck in the back of my mind. And that was, with new instruments, you do new experiments. This then allows users of the facility to come there and do new experiments at the facility and train graduate students. And that's really important for the future of fusion, is that we have gifted and talented young people that understand the science and understand what the issues are associated with trying to advance the bigger objective of fusion energy. So I would say there were three aspects of it, but even then there was another one which came up, and that had to do with the international nature of D3D. What we did was we made D3D essentially a 24/7 facility where it worked with China while the Chinese were asleep. And we're able to conduct experiments on their machine called EAST, and then at the same time reach further east to ITER, to be a kind of a center that coordinated research across an enormous number of time zones. So, you know, it enabled the facility to be much more productive and a contributor to international science as a whole. So, you know, it's quite gratifying. And, you know, the people there, extremely dedicated, very, very bright people. They understand the science really very well. And I was always very proud of being associated with D3D.
Well, and so at D3D, there was also a lot of innovation going on. And so a couple of things that you'd worked on were a waste burning reactor and then meltdown proof nuclear fuel. And now the meltdown proof nuclear fuel, that's not fusion, right? That's standard fission.
That's fission. And you have to clarify this meltdown aspect of it. The key, in my opinion, to the advancement of fission, like any technology, is materials. If you want to change the performance of something, you have to look for new materials that can support that performance. This is the way technology evolved over the last couple hundred years. It's the materials and the knowledge that you derive from understanding them that's used to exploit them in applications. This is the way technology evolves. Now, in the case of fission, there are two characteristics of fission that we focused on at General Atomics. One is temperature. If you get to higher and higher temperatures where you can produce higher temperature heat, quality heat, that can improve efficiency because you're putting more energy into the medium that drives, say, a turbine generator, okay? You're getting more value out of the investment you make in the reactor by going to high temperature and exploiting the heat from it, okay? That drives down the price of electricity. That's what that does. It's very important. It's fundamental to all heat engines, okay? Not just what we were doing at GA. The other is radiation resistance. By that I mean you want materials that can maintain their integrity, not just in terms of temperature, but also radiation damage. And because you're in a nuclear reactor, you're in a very harsh environment where neutrons are bombarding the material and potentially essentially wearing the material out, essentially
Yeah.
causing damage, right? And so what you'd like is a material that's radiation, what I call radiation resistant, so you can keep it in there longer. The advantage that that has is that you can burn the fuel longer and you can get more energy out of the fuel. So these two things, temperature resistant, radiation resistance, are essentially synergistic. They have the potential to reduce the price of electricity, but also the amount of fuel you need in order to produce the equivalent amount of electricity, okay? And so this is what we focused on. Now, an offshoot of that is what some people call meltdown-proof fuel. It's really accident-tolerant fuel. And I led the creation of that program in collaboration with Congress to try to push in developing a fuel that would be less vulnerable to failure. Now, the type of failure we were looking at is related to what happened at Fukushima. At Fukushima, some people may recall that there were these explosions that occurred. These were hydrogen explosions.
Yeah.
So what happens in a conventional reactor that's water cooled is that the fuel is inside a metal cladding. And unfortunately, as the temperature goes up, that metal oxidizes with the water. So you have water reacting with the metal, and what it does is produce hydrogen. Remember, water is H2O. So the oxygen goes to the metal and the H2 gets vented. If that accumulates inside the containment vessel, and any oxygen that makes contact with it can explode, right? And so we decided to see if we could develop an accident-tolerant fuel that would prevent that type of catastrophe. Now, it turned out that the material we were focused on for this high-performance reactor, this is called silicon carbide, has very interesting properties. One is it has a melt temperature at 2,700 degrees centigrade. Ordinary metal starts showing fatigue at about 800 degrees centigrade. So you're talking about more than a factor of 3 higher temperature resistance. What this does is it builds in headroom between the failure of the reactor and the material, okay? And so you build in some cushion in regard to that. The other thing is that we believe, based upon the properties of silicon carbide, that it didn't react with water. So that meant that we could completely eliminate the hydrogen production problem in an ordinary light water reactor. And so I managed to convince Congress that this was worth pursuing, and that created the Accident Tolerant Fuel Program. And there are various approaches that are being taken right now, silicon carbide and then metal coatings, for example, to put on top of the metal that normally is used in a nuclear reactor to fuel, to try and deal with the problem, okay? And so these are being pursued. At the same time, we came up with a revolutionary new reactor. It's called Energy Multiplier Module, or EM squared. And EM squared was a fascinating design. It had certain characteristics that we convinced ourselves were a radical change from current nuclear technology, nuclear fission technology. One is the reactor was the size of a school bus, okay? So when we designed it to be truck transportable. on a highway system. We even designed it so that it could go under bridges, overpasses, okay? The other thing is that in order for it to really be able to compete with other energy sources, it had to have a high power density. And that had to do with being able to pack fuel into the reactor. And we picked a particular fuel, uranium carbide fuel. See, silicon carbide is a ceramic, okay? Uranium carbide is also ceramic.
Okay.
Both of these have very high melt temperatures. So the synergy was there in terms of the temperature resistance, but also uranium carbide has a very high packing density. You can pack a lot of fuel in a small volume. So that helped in terms of the nature of the reactor and making it compact. The other thing is we could go to high operating temperature. So we were able to go up to 850 degrees centigrade operating temperature. Typical light water reactors that are out there deployed are at about 275 degrees. This can dramatically improve your efficiency. A typical light water reactor has an efficiency of about 33%. And that hasn't changed in 60 years, right? Our reactor could get up to 53%.
Okay.
So what this does, it has two effects. One is it can drive down the price of electricity. The other effect is it produces a lot less nuclear waste, okay? Because you need less fuel to produce the same amount of energy. And the other thing about EM square was silicon carbide is radiation resistant. And the reason why we know that is because Oak Ridge National Laboratory has had samples of uranium carbide in its test reactor for decades. And they have been testing the material to see whether it maintains its integrity over long periods of time in a harsh radiation environment. And all indications have been that it is. So we predicted that silicon carbide could maintain its integrity in a reactor for 30 years. This implied that if you put enough fuel in the reactor and you design the core in a very interesting way, you could have a reactor that can burn for 30 years without refueling.
Okay.
So an ordinary reactor, you refuel the core over a period of 4.5 years. So this gave us a factor of 6 increase in time span for the fuel to stay in the reactor. This meant that you could get more value out of the fuel. You'd burn more of it. And so again, you don't need as much fuel in a sense to produce the equivalent amount of electricity. So the amount of waste also is less. We could reduce the waste by 80% with EM squared. And so EM squared, by its design, is a revolutionary reactor that's driven by new materials and new knowledge that we managed to acquire to exploit the material, you know. And so we just found another application of it in accident tolerant fuel.
Yeah.
So it really is an exciting project. Unfortunately, when we entered the competition at Department of Energy for a innovative small modular reactor, as typical, you know, the US Department of Energy always thinks in the past. That's what it does. And so it picked a light water reactor design that was small. That's new scale. And in fact, it has less efficiency than a large light water reactor. In fact, you need 6 NuScales, 6 of them, to produce the equivalent amount of energy at 1 EM squared.
Ah, okay.
But DOE felt that EM squared was too risky. And so, you know, in a risk-averse world, you make choices, okay? And everything we said about NuScale in terms of, you know, its cost and efficiency and low power, et cetera, has turned out pretty much to be true. So, you know, EM squared would have been a way of pushing out the performance of technology dramatically, largely because of the materials and the design of it, you know, so.
Yeah. Well, let me jump back into fusion for a sec, because again, I mean, and you have so much experience, I guess. One of the things is it's difficult for me to focus in on this, but let's focus back in on fusion. So Popular Mechanics just ran an article on the new MIT Spark reactor, and they were claiming that they think that could be up and running within a decade. I guess the scientists on that project said that. What can you tell me about this compact fusion reactor compared to the traditional Tokamak that I think we're all familiar with?
Yeah, well, it's interesting because what I recall vividly was a meeting that was called in Washington, D.C., where leaders of fusion in the United States were asked to come to educate congressional staff on the various approaches to fusion. And DOE organized this. And I gave a talk there, was on D3D and its role in the fusion enterprise, how it was supporting ITER. And at that meeting, Dennis White got up and began to talk about using high temperature superconductors to design a new fusion tokamak. And this was not a new idea. You know, I, along with people at GA, you know, toyed with this idea. But, you know, the problem is if you're focused on a particular path to a major technology development, it's very difficult to divert your attention away from it and just switch gears to something like high temperature superconducting magnets, okay? In the case of MIT, unfortunately, they were losing their test reactor there because DOE decided it didn't want to fund it anymore. That was CMOD, which, you know, was a workhorse for the, not just MIT, but for the fusion community for many years. And this gave, like a crisis, it gives rise to an opportunity to try and do something different. So Dennis got up and he gave this really wonderful talk about using high temperature superconductors. And of course, you know, people that understand the physics of fusion understand that high temperature superconductors can produce magnetic fields that are twice that of standard superconductors. Well, if you can do that, everybody in the field knows that the power density of a fusion reactor goes like the magnetic field to the 4th power. So simple arithmetic is if I multiply it by 2, that means the power density goes up by a factor of 16. Now, of course, that's theoretical. There are other things that enter into it. But getting a factor boost like that is enormous. I mean, that's a tremendous advancement if you can do it, right? So Dennis, who, you know, is a very smart, ambitious guy, I met with him about a year ago when I was at MIT, is, you know, a driving force behind this. And Spark is a very innovative well, it's an invention, it's a new invention,
Yeah.
and so it has enormous potential to impact. Now, you said 10 years. Well, I think, best as I can recollect, they want to be able to demonstrate a burning plasma by 2025. ITER wants to have a first plasma by 2025, which means put the plasma in and show that you can have a plasma inside of ITER. So Spark's goal is much more ambitious than that of ITER over the same time scale. So Spark is really an ambitious venture to try to see if one can achieve a sustained burning plasma. Of course, as I recall, Spark is talking about 10 seconds for the duration of the burn based upon the design they have. ITER is eventually going to try to do 500 to 1,000 seconds. So you heat the plasma up to the temperature, you get it started, and then you stop heating it and it self-heats. And in the self-heating, it produces thermal energy, okay? And it sustains itself over a long period of time, remains stable, So either one of these would be a major achievement, but I would think Spark, if it does it, that is extraordinary, that they could accomplish that.
Yeah. Well, so the big science research establishment has been pursuing tokamak style designs for about 50 years now. And critics of this have said that other approaches to controlled fusion need more attention as well. What is it about the tokamak design that has the fusion establishment so focused on it?
Yeah, well, you have to go back a little bit in history, and it predates me. The genius behind DIII-D was a Japanese physicist who was at General Atomics. His name was Tohiro Okawa. He's a plasma physicist, is very well known. He assembled an extraordinary team of people at GA, very gifted and talented people. One in particular, who wound up being my chief scientist at General Atomics, is a guy by the name of John Rawls, brilliant fellow. But the genius behind it, the idea, was Okawa. And what they did was they developed, small scale experimental models that led them eventually to the D shape. That's the D in DIII-D. It's a D shape, which convinced them that that was the geometry for the tokamak that would work in terms of trying to contain and stabilize the plasma. That D is the D of ITER. ITER is a scaled up version, basically, of DIII-D. East in China is also a D shaped. So tokamaks derived their D shape from the original work at GA.
Yeah.
Okay, General Atomics. So that's the reason why it's considered to be important, and in its role in influencing the progress of.
Well, what do you think about IEC fusers? I wanted to ask about that. Like I'd mentioned to you earlier, Robert Bussard had the Polywell design, which was more magnetic, but then, there have been so many different variations on IEC fusers, and those things, they were demonstrating fusion back in the 50s. I think the challenge was always the efficiency and,
Right.
could they actually get anything out of it, right? Do you think there's a future with those?
Yeah, I'm not an expert in that, but I understand the concept that they had. It's not really difficult to understand. I mean, they have a spherical chamber, right? Spherical chamber, sphere. Inside of it, they have spherical wire cages that are nested within each other, smaller one and a larger one, right? And the idea is you inject the fuel in it, you heat it up and then apply a voltage that'll strip away the electrons and drive the fusion ions towards the center of the sphere where it becomes concentrated, and they collide and they fuse. And from that, you would derive the energy output, right? But as you point out, all these devices have problems with gain because there are losses associated with it. As far as I know, the progress on limiting those losses has been also limited with these designs, but the one good thing is, and I always emphasize this, multiple approaches to the same problem are very beneficial because they teach us about what works, what doesn't work, and why it doesn't work. So science isn't just about success, it's also a lot about failures and what you learn from them. And so the various designs that are out there are a good thing, because they teach us something about the limits of what nature will allow us to accomplish, and people point out that, the sun is a huge fusion reactor, right? Well, it is. And there are about 1 billion trillion of them in the universe. They're called stars, right? But the fusion reaction used on the sun is very different than the one that humans came up with on Earth. Because the sun doesn't have deuterium and tritium, which are two versions of hydrogen. It just has hydrogen. And the fusion reaction on the sun is very slow. And the way the sun gets over this is because it has an enormous amount of high density hydrogen that is close to the center of the sun. And that enables a lot of very slow fusion reactions to take place. But the reaction that we predict on Earth is 1,000 times more productive than that on the sun. That's what provides the motivation for fusion on Earth. It's that factor of 1,000. Because the problem you have is the sun uses gravity in order to compress the material, so that the density of mass in the center of the sun is about 150 times that of ordinary water. We don't have that luxury on Earth, right? So we have to try to figure out, okay, how dense can you make the fuel, right? And so that gets you into how to contain it, right? And the problem is in a tokamak, the density is very low of the fuel.
Yeah, actually, that was my next question. Was you've said that fusion has a relatively low power density, and so if you want lots of power, you need a big system. I'm wondering if you could kind of elaborate on this, and I also wanted to ask if you were able to do something like direct electric conversion rather than turning a steam generator. Do you think that would change the output? Is that even possible?
Well, yeah, the obvious consequence of your last statement, right, is you wouldn't have a turbine generator. And turbine generators are huge. They're, it's not so much their mass, but the volume that they have, especially when you go to higher and higher power. The weight goes up, the volume goes up. These are big devices, rotating devices, right, that you essentially use steam to drive them, right, to spin them so they produce electricity. So if it was direct, you'd eliminate that, which would be a significant savings, right? The issue of power density really is about watts per cubic centimeter, say, or unit volume, whatever units you want to pick, cubic inches, whatever, doesn't matter. But, you know, what you're looking for is a high power density. Why? Because for the total amount of power, if I have a high power density, I can produce it in a smaller volume, which means less material. I don't need as much material or size to produce the equivalent amount of power.
So that's where superconductors come into this, right? And Dennis White he's pushing,
Right.
yeah.
Exactly, because as I said before, the power density of fusion goes like the magnetic field to the fourth power. So you're multiplying something 4 times. If I double it, that's 2 to the fourth. 2 to the fourth is 16. That's the number 16. That's a huge factor. And you could take advantage of that by reducing the volume to produce the same equivalent amount of total power, and hence drive down the cost. Of course, that's part of the economic equation. There are other parts of the economic equation that matter, okay? So you have several problems that affect a device like Spark or ITER or any Tokamak, right? One is you have high energy neutrons that are basically being produced that you want to capture their energy. They have to pass through the first wall. When they pass through the first wall, they do damage to the first wall. Okay. Eventually that damage becomes unsupportable. So you have to shut down the reactor and remotely go in and replace all the wall, right? So that affects what's called the duty cycle. How often is the reactor producing energy, right? The downtime, you want to minimize it, right? The other is the neutrons, you want to capture the heat. So you need a material on the other side of the wall that will slow them down and capture the heat up that, which will then heat up a gas or produce steam at high temperature that will drive a turbine generator, as we discussed before.
Yeah.
The other problem is, which is a significant problem, is that tritium is not a naturally occurring substance on Earth. It's produced up in the upper atmosphere by cosmic rays that essentially are protons from distant stars that are impacting the top of the Earth's atmosphere, and it produces tritium. But tritium, you know, we can't go out and find it, right? You produce it, right? We do produce it in the United States, but we produce it for the weapons program, okay? Nuclear weapons program. It's very expensive to produce. A pound of tritium costs probably on the order of about $30 million to produce.
Wow.
It's the most expensive material on the planet Earth, okay? So what you have to do is figure out how to produce it economically. Now, people understand how to produce it. The issue is, can you produce it economically? Well, the answer to that has to do with lithium. Okay? There are vast abundances of lithium in mines in the ground, as well as lithium in the ocean. The problem is, you're interested in a particular isotope of lithium. And there are various isotopes. The one you want is lithium-6. The dominant one is lithium-7. So you have to separate out the lithium-6 from the lithium-7 so that you can then convert that lithium-6 through neutron bombardment into tritium. So the material that's in the blanket contains lithium-6. The neutrons will impact it, tritium will be produced, but then you have to chemically purify the tritium and feed it back into the reactor. So this way, it's a self-sustaining system. It's sort of like, you know, the ancient Ouroboros, which, you know, from mythical ideas of a the snake that lives forever by eating its tail.
Yeah, yeah.
There's that symbol, that people have, is a similar idea to EM squared, by the way, energy multiplier module, because the idea behind energy multiplier module was also to recycle the fuel, because in one load of EM squared fuel, that could last 200 years. Okay, so through recycling. So you would recycle it 7 times, essentially, and extract the original energy out of the core. So in itself, it's an Ouroboros. It feeds off itself, makes its own fuel, and then works that way. The same is true for fusion. But then, you have to demonstrate that all of this will work and work economically. So you have the wall is one problem. You have tritium production is another problem. And then the other problem is getting to high efficiency, to convert as much of the heat that's generated into electricity. These are real challenges. These are practical challenges associated with fusion. Now, if you could do it directly, the problem is neutrons can't directly or are ineffective in directly creating electricity. So, people have come up with other schemes to try and do this. There's a design, which is a proprietary design, which I, don't know the details of, but it's called tri-alpha, where essentially you accelerate a proton to collide with a boron plasma. And when you do that, you can create 3 alpha particles that are charged.
Okay.
So those alpha particles are electric. And so there are various ways you can convert that directly into electricity. Now, the challenge with that type of design is the temperature that you have to get to. So the temperature in the center of the sun to create fusion is 15 million degrees. Okay. In a tokamak, it's about 200 million degrees. Okay. In tri-alpha, you're talking about 1 billion degrees to get to a temperature. And that has to do with the proton and 5 protons in the boron nucleus. They repel each other. But to have fusion, you have to overcome that repulsion. That repulsion relates to the temperature. And so there, there are other ways of trying to do this. And this gets back to my statement I made before. Multiple approaches to trying to address these type of things is a good thing, because people can learn what works and what doesn't work. So tri-alpha might turn out to be an advantageous way of improving the efficiency of conversion of primary energy into electricity.
So John, let me close out with that in terms of fusion. Now, I did want to ask you, and sorry, are you still with me?
Yeah.
Oh, okay. Your camera paused for a second. Sorry. I don't know if you'd be open to talking about it or not, but you'd mentioned working on particle beam stuff. I don't know if that's something you'd be open to talking about or not. Just chit chat, because I don't have any questions written about it. But
well, there are people that talk about transmuting reactors where they use an accelerator to try to produce impacted material like bismuth or something to produce neutrons that you then convert into thermal energy.
Oh, well, and so, but I mean, you were talking about SDI stuff, right? And that was interesting because
it never made any sense. It never made any sense. There's a simple reason why, from an engineering standpoint, it doesn't make any sense. The problem is, you want to project these beams over long distances.
Yeah. Yeah.
Okay. Well, in order to do that, where you can efficiently deposit the beam energy on the target, you have to go to high energy. This has to do with the divergence of the beam. There's an inherent divergence that occurs, and I can't go into it. It has to do with quantum mechanics, where you wind up with an inherent divergence in the beam. And of course, what you want to do is keep the beam as narrow as you possibly can, okay, from its production end. That turns out to go like 1 over the square root of the energy of the beam. So as you increase the energy, that angle goes down. The reason why you want the angle to go down is because when you project it a long distance, it widens, okay? And it covers a larger area, right? And your objective is to deposit as much energy as possible on the target.
Yeah. Yeah.
Beam diameter can grow in size. That's, enormous, and you won't deposit anything. Now, if you get to high enough energy, you can overcome that.
Yeah, it self-focuses.
Okay, but the problem with that is the target that you're going to hit becomes more transparent. In other words, the beam easily passes through it without depositing any energy. So from an engineering standpoint, it doesn't really make much sense, okay? And the papers that I wrote, along with other colleagues at MIT, and the one I published in Scientific American, I think it was around 1980, points all of this out.
Yeah.
These things don't make any sense,
Well, I mean, if it's okay, can I run? I could be off base on this, but I'm bringing kind of two things together, and I know I'm kind of going off track. I've already got our interview stuff. That's why I'm kind of taking this the other way. But when you mentioned particle beams, this was okay. So right now, the U.S. and China are both playing with these solar. Basically, they want to use lasers or masers to send energy from space down to the Earth, right? And the concern is that these are dual use technologies. So if you can send a maser down to power stuff, you can send a maser down as an EMP, or maybe even to destroy stuff. But again, you've got issues with the beam spreading and stuff like that. So my thought was, the minute I heard this, I said, wait a minute, laser, if you can send a laser down from space and it's high enough energy, do you think it's possible that you could short circuit the ionosphere to the ground and create lightning, create an electrolaser?
I doubt it. I mean, the problem with all of this, I learned something very important while I was at General Atomics, which I sort of knew even before I got there, because, I've run a small business with my wife, and I understand accounting and how to make a payroll, how to make a profit, and all of this stuff.
Yeah.
And the question becomes an economic one as to whether it makes any sense to do this kind of thing, And my own view of this is that trying to generate power from space to beam it down to the Earth is extremely complex, and it's very operationally intensive, and costs associated with it will, I think, prevent them from being viable, okay, as sources of energy. Natural gas power electric power is the benchmark that everybody should be using to try to figure out whether they have a competitive source to produce economically produce electricity. This is what we used at General Atomics. Our goal was to see if we could compete with natural gas plants. Natural gas plants are hard to beat. They really are. They take maybe a year and a half to build. Okay? The risks associated with building them is low. The price of the resource is relatively low compared to
Yeah.
historical levels. The efficiency of a natural gas plant is about 63%, right? There's no other source that has that level of efficiency. I mean, we can only get up to 53% with EM squared, right? And in order for EM squared to compete with a significantly compete with a large light water reactor, we have to gang up 4 of them together in one system. And then we can undercut the price of that electricity by 40%. So instead of it being 10 cents per kilowatt hour, we could get it down to 6 cents per kilowatt hour, which gets close to natural gas, right? But the risks involved in building nuclear plants is much higher than it is for a natural gas plant. And so that's the reason why utilities who have to invest real money into energy sources have been moving away from coal to natural gas. And natural gas is king as far as, producing electricity. Even when you deploy renewables, you need baseload in order to be able to deal with the intermittency of renewables. The duty cycle is only 30%. Right?
I see what you're saying. Yeah. Yeah.
So you have to co-deploy them with a baseload. Typically it's natural gas. Most people don't know this, but it is, and you need something that's scalable, and, natural gas has a problem in that, the natural gas distribution system is not all that elaborate, right? Because you have to supply the gas to the natural gas plant. But there's a lot of incentive to invest in that infrastructure to be able to supply the natural gas to the plants.
Yeah, yeah.
So that's the problem that any energy source that you propose faces. Can you make it economic? If you can't, nobody's going to take real hard-earned money and invest it to, produce electricity. The same will be true for fusion.
I know. I see what you're saying. Yeah.
If nuclear energy was competitive with natural gas, my bet is people would easily invest in nuclear energy. Okay. And there are reasons for that. The plants last a long time. You can get payback over, say, 10 years, and then the rest is gravy, and run them for 40 years. So, but they have to be economic.
Yeah.
And that's really the problem. You have a large resource. I mean, if you go and sit down and do some simple calculations, right? Based upon known reserves, right? You have about easily 10,000 years of nuclear fuel that you can explain. That's just known reserves. You can dig deeper and find more, okay? But that's just known, what you could extract. Fusion, about 20,000 years you have in terms of known reserves of lithium, So you have, substantial amounts of resource that are there. The thing about natural gas, which is a bit negative, is it's used for other things. So natural gas is used in the production of fertilizer, for example, which is vital to the agricultural industry, right? It also is used by chemical plants to produce process heat to facilitate chemical reactions,
And it's produced from petroleum too, right? So it's not renewable.
That's right.
Yeah.
It's potentially an exhaustible resource. So you'll have to, be careful about, because of these other uses of it that are vital for any economy, So, so it's not all that simple.
Yeah, no, and it's an intriguing perspective. And what I'll do is I'll put your thoughts in on natural gas. I'll add those in too, because I think that's a good way to kind of offset and say,
Here's something that people don't think about, okay? That is simple to understand. It's not complicated, right? So if you look at how our electricity production takes place in this country, if you were to take away all coal plants, eliminate all of them, right? And nuclear plants, which will be eliminated because their licenses expire between now and 2050. So let's suppose coal and nuclear were eliminated.
okay,
By 2050, you would have a 53% shortfall in electricity production. Okay? Now, let me make one simple assumption on top of that. Suppose electricity demand in the United States increased by 1% per year between now and 2050. The shortfall in electricity would be over 90%. How are you going to replace it? So if you're talking about taking just renewables and doing it, you would not only have to replace all of what already exists, but you would have to, on top of that, replace what's lost, right? In terms of, the electricity needed for a growing society, right? It's infeasible. It doesn't really make much sense, okay? So at the end of 2050, we would be left with just renewables and natural gas. That's all we would have. And my judgment is that people would be experiencing a lot of brownouts during various times of the day in various parts of the country, unless something major was able to overcome that. And I don't know what exactly that would be, so nuclear is important, right? Fusion could be important, but the major obstacle there is demonstrating that you can have a sustained burning fusion reaction. That's what ITER is about. ITER isn't about producing electricity. It's not. It's not going to, it won't be capable of producing that electricity. It's about demonstrating that you can have a sustained burning fusion reaction. That's what its goal is. If it demonstrates that, it helps all of fusion, all ways of producing fusion. Now, Spark succeeds over the next 5 years. That would be an extraordinary accomplishment. And I wouldn't bet against MIT, okay? I'm not saying that they'll achieve it, but the people there are very smart, creative, and adaptable. And the advantage that they have that ITER doesn't have, they're small. They can move quickly to try and solve problems.
Yeah.
And maneuver to try and be inventive of how they solve problems. ITER is a big, large organization with 6 nations and the EU all involved in a giant project, which is very difficult for it to have any agility at all, and so I wouldn't rule out Spark. And might be a big surprise, hopefully. So,
Yeah. Well, John, thank you. Thank you so much for your time. So here, I'm going to stop recording now.